Hello students, now we are going to talk about the problem on dictionary attack in passwords. So let's go through this. We have a kind of password file that contains 2 to the power 10 hashed passwords and a dictionary that contains 2 to the power 20 words. Okay, so what we want to determine is the number of hash computations that one has to do in order to find, for example, the password of any user in this password file. So the attacker is not really interested in any specific user's password in part A. He is interested just in finding the password of any user so that he can log in as that user. Okay. So this file contains several entries with the hash value of passwords. So the attacker is interested in trying to find the password of any user, right? So which means any entry, not a specific entry. So the strategy is I'll take one word. Okay, so take one word from the dictionary, compute its hash value, and see if it matches with any of the hashed passwords stored in the password file. If there is a match, we are done, or the attacker has managed to find a password and he can log in as the user corresponding to that password, right? So we are interested in finding what is the number of hash computations it takes on average to do that. Okay, so if you notice, I gave you this formula where the average number of hash computations to be done to crack the password of any user is basically the size of the dictionary divided by the probability that any chosen password is in the dictionary. Okay, so what it means by the probability is we are not sure 100% whether any of these passwords that are stored in the password file or in the dictionary or not. So what is given to you is the probability that if I pick any password from this password file, the probability that it comes from the dictionary is this 1/4. Okay, so the 1/4 given in the problem statement is the probability that any given password in the password file will come from the dictionary. Okay, and it is with a probability of 1/4. So we can say that the number of hash computations needed to crack the password, again average number of hash computations, is size of the dictionary divided by the probability that it comes from the dictionary. So this is the size of the dictionary, 2 to the power 20 divided by 1/4. So 1/4 is 1 over 2 square, right? So that's like telling something like this. So we have 2 to the 20. So that's this exponent over here. And then you have 1/4. So that is equivalent to writing something like 2 to the 20 again. This 1/4, actually I can take it to the numerator and say this is 4 times 2 to the 20, so that keeps it easy to visualize it. So I can write my 4 as 2 square times 2 to the 20, so that's going to be why it is 2 to the 22. All right. Okay. So that is the A part. In B part, we are trying to find the password of a specific user or a particular user, say the root, right? So we are not interested really in any entry. We are interested in a specific entry in this password file that corresponds, say, to the root user. Okay. So what we have to do, again, choose every word in the dictionary, find a hash value, and see if it matches with the hash value for the root's password. Okay. So you could try all these words in the dictionary, but again, the probability that this password of the user is in the dictionary is only 1/4. Okay. So there is a 3/4 probability that this password will not be in the from the dictionary. So in that case, what you have to do? We have to do a brute force approach of trying to crack the password. So if if the root's password is not from the dictionary, then the attacker has to resort to a brute force approach of cracking the password, right? So which means the complexity involved now is going to be a mix of both, right? So the average number of hash computations is going to be something like this. You can search from the dictionary, right? So average number of hash computations to crack the password using the dictionary attack. So that he can do with a probability of 1/4, and then 3/4 the probability to crack the password using a brute force attack. Okay. Now, what is the average number of hash computations to crack the password using the dictionary attack? We just found it is what going to be, because it could be any of those 2 to the 20 words, right? So the dictionary is of size 2 to the 20 words, right? So in order to crack this particular password of the root, at the worst case, you will try all the 2 to the power 20 passwords. On average, you will try half of these passwords from the dictionary and see if it could be the root's password. So if you are successful, on average, you would try only half of these. Okay, so that's why the average number of computations to crack the root's password using the dictionary attack is going to be 1/4 times this, or not this. I'm going to just copy this from here. Let's see. Two to the 20 over 2. Okay. So this is the average number of hash computations that he has to do to crack the password using the dictionary attack. Why? Because again, in the worst case, he would have to try all the passwords, all the words in the dictionary, On the average, he has to try only half of them. So that's going to be 2 to the 20 divided by 2. So that's found to be 2 to the 19, right? So one part of the expression is 1/4 times 2 to the 19. So now we are interested in finding what is the number of hash computations needed to crack the password when it is not in the dictionary. When it is not in the dictionary, you have to resort to a brute force approach. Now you have 128 characters that could be part of the password that's given to you again in the problem statement. The password is chosen from a 128 character set and the length of the password is 8 characters. So again, going with our n over L formula, if you have 128 characters to choose from, here your n is going to be 128 and L is going to be 8. So it's going to be 128 raised to 8. That is the search space, which means the maximum number of passwords you will have to try. Okay, and again, on average, you will be able to try only half of them and find the right word or the password, right? So the search space is going to be the maximum number of passwords is going to be 128 raised to 8. Now 128 can be written as 2 raised to 7. So it's basically now 7 times 8 is 56. So 2 raised to 56 is the maximum number of passwords you will have to try at the worst case. On average, half of these words could be tried and you could have cracked the password by the time. So that's how you get 2 to the 56 divided by 2, which is 2 to the 55. So 1/4 times 2 to the 19, it is the number of hash computations you do on average to crack the password from the dictionary, and this is the number of hash computations you do if the password is not from the dictionary. Okay, again on average. So you're basically now simplifying these two expressions, these two terms. So 2 to the 19 divided by 4, which is 2 squares, so this is going to be 2 to the 17, and this is basically 3 times 2 to the 55 over 4. Okay, so this is going to be 2 to the 17 and then we have 3/4 times 2 to the 55, so that's going to be 3 times 2 to the 55 over 4. So 4 is going to be 2 squares, so this is going to be 3 times 2 to the power 53. Okay, so now what I'm going to do is, so this is what we have here now, right? So I want to have this 3 written as 2 raised to something, so that we can kind of have everything in terms of like 2 raised to something. Okay, so we want to represent this 3 as 2 raised to some exponent e, and we want to find not e, let's say some x. So we want to find, let's say, what is that x. So we want to kind of solve for x over here. Right, so now if you know logarithms, we'll take log to the base 2 on both sides. Okay, so we get something like this. So this is to the base 2 and log to the base 2 for what? This. Okay, so basically now from again logarithms, we know this term could be written as x times log 2 to the base 2, so that is going to be x is going to be log 3 to the base 2, and logarithm of anything to any base, so the formula is, let me give you a general formula. If you want to find the logarithm of say a to the base b and your calculator doesn't really have that base, the formula you can use is going to be log of a to the base, say, so 10, then log of b to the base 10. So this is the kind of formula that you can use to compute the log of a to the base b, right? So now what we want to find is log of 3 to the base 2. So we want to find log of 3 to the base 2. So this is basically log of 3, I believe this should be 10 to the base 10, and this should be 2 to the base 10. Okay, so I think I have recorded it as O, right? So log of 3 to the base 10, if you use your calculator, is going to be 0.47712, and 2 to the base 10 is going to be 0.30103. So if you do the division, you'll get 1.5849. So that's the number I have over here, right? So that is what we have over here. So now everything is in kind of 2 raised to something. So now this term is 2 raised to 1.5849 times 2 raised to 53. So I can add this 53 and 1.5849 and say this is 54.5849. Okay. So just by looking at this, you can say that this, between these two terms, 2 raised to 54.58496 is more dominating compared to this, right? So I can say this is kind of approximately equal to 2 raised to 54.58496. Okay, and again another approximation, as I said, this is kind of adding some little quantity to it. So I can say it is 2 raised to 54.6. You know, this 2 raised to 17 is very insignificant compared to this, but it just does increase the value of the total by a little bit. So I can say instead of 54.58, I can say it is 54.6. Okay, that's the kind of approximation. So this is the number of hash computations you do to find the password of the specific user. In this case is going to be the root. All right.